Okay, we are going to do a quick review of significant figures. So significant figures are the digits in a number that are meaningful. And in science, not all digits are meaningful because they are measurements, not exact values, like in math. So in math, you're working with exact values. All the numbers are meaningful. In science, they aren't. So we have to use significant figures so that when we're doing calculations, our answer is not more or less accurate than the measurements we used in the calculations. So there's 4 rules for significant figures. The first rule is that all non-zero digits are significant. So anything that's not a zero is significant. So this number has 3 digits, none of them are zeros, so it has 3 sig figs. The second rule is that all zeros between non-zero digits are significant. I call these sandwich zeros. So if there's a non-zero and a non-zero and some zeros in between, the in-between zeros are significant. So 1 and 2 are definitely significant because of rule number 1, and the sandwich zeros are also significant, which means we have 4 significant figures in that number. Zeros before the first non-zero digit are significant, or not significant, sorry. So that means front zeros, they don't count. So all these zeros that occur in front of the first non-zero digit are not significant. So not significant, not significant, not significant. The 2, the 9, and the 1 are significant because of rule number 1, and these zeros in between are significant because of rule number 2. So we have a total of 5 significant figures in that number. The last rule is that end zeros, zeros after the last non-zero digit, may be significant. They are significant if the number has a visible decimal. So if we look at this example here, there's a visible decimal right here. So that means the zeros at the end are going to be significant. Now the front zeros are never ever significant, even if there is a visible decimal. So these 3 are not significant. The 2 is definitely significant because it's not a zero. And the end zeros are significant because there's a visible decimal somewhere in this number. So this number has 3 significant figures. In this number, there is no visible decimal, so those zeros at the end are not significant, which means this has only 1 significant figure. So there's some examples here. You might want to pause the video and try these examples out for yourself. So I'll go through the answers now. 3 non-zero digits, all 3 are significant. This number has zeros at the end and no visible decimal, so only 1 digit is significant. This is not the proper way to write this number, but since there is a visible decimal, the end zeros would be significant. So this would have 3 sig figs, but technically it should be written as 3.00 times 10 to the power of 2 if you want it to have 3 significant figures. So you want to switch it into scientific notation. This number has a front zero. Front zeros are never significant. Non-zeros are always significant, so 3 significant figures. Front zeros are never significant. Sandwich zeros are always significant. Non-zeros are always significant, so 3 significant figures. Front zeros are never significant. Non-zeros are always significant. And end zeros are significant if there's a visible decimal in the number, so 4. Now when you're doing calculations with sig figs, if you're adding and subtracting, you don't actually have to look at sig figs. You look at decimals or place values. So in this example, if there are decimals, the easiest way to do this is just count the decimals, how many numbers occur after the decimal, and then your answer should have the least number of decimals. So here we've got 3 numbers after the decimal, here we have 2 numbers after the decimal, 2 is less than 3, so our final answer should only have 2 numbers after the decimal. So when we add these together, I always write the full answer and then I round. So when I add them together, I get 0.145, but I know it should only have 2 numbers after the decimal because this number only has 2 after the decimal. So I need to cut the number off here. But since the next digit is a 5, that means I have to round up. If it's 5 or higher, we have to round this number up. So it becomes 0.15. When you're adding and there's no decimals, then you have to look at the most or the least accurate place value. So this is the ones place, and this one, the last non-zero digit is in the tens place. Whichever one's further to the left is the less accurate one, so that's the one you go with. So since the tens place is further to the left, our answer should only be accurate to the tens place. So 665 is the answer. We want to cut the number off here, but we can't just cut it off to, well, first of all, this is a 5, so we're going to be rounding that up. But we can't cut it off to 67. That's not the same as 665. If I said I was going to give you $665, but I'm going to round it, and I gave you $67, that wouldn't make much sense. So instead what we do is we write down the 67, and then we use a 0 as a placeholder, so it still has the same value as before, 670. When you're multiplying and dividing with significant figures, you do look at the significant figures. So your answer should have the same number of sig figs as the least number of sig figs in the question. So again, I always start by just multiplying these out and writing the full answer. So you can do this on your calculator and just write exactly the number your calculator gives you. And then I round it. So I count how many sig figs each of these numbers have. So front zeros are not significant. So this has 5 sig figs. Front zeros are not significant, and zeros are significant if there's a visible decimal. So this has 2 sig figs. 2 is less than 5, so my answer should only have 2 sig figs. Since front zeros never count, 2 sig figs starts here, 1, 2. So we want to cut the number off right there. And since 9 is the number immediately following, we need to round up that 3 to a 4. So 0.044. And then do the next one on your calculator. And I got 85.6745. And then count your sig figs. This has 3 sig figs because the end zero is not significant since there is not a visible decimal in the number. This has 5 sig figs. Front zeros don't count, sandwich zeros always count, end zeros count if there is a visible decimal. So 3 is less than 5. My answer should only have 3 sig figs. So I count 1, 2, 3, cut the number off here, 85 point, and I have to round up, 7. If you are adding and subtracting all together, then you just have to do it in your BEDMAS order. So brackets, exponents, division, multiplication, addition, and subtraction. So you would start by multiplying these two and writing the answer to that without rounding, but just underlining the proper number of sig figs. So I'll just do that real quick. I get 14.5992, and I know it should only have 3 sig figs because that 4.00 only has 3 sig figs. So I underline those 3 sig figs, and then I add these two numbers together, but I add that full number, not the rounded version. So my answer is 14.9092. Then I look at decimals because I'm adding. This has 2 numbers after the decimal. This only has 1 significant number after the decimal. So I have to cut it off at 1 number after the decimal, which would round to, well, it rounds to 15. Oh, sorry, no, 14.9. Because it's a 0, we're not rounding it. If it was rounding to 15 and we needed 3 sig figs, or sorry, 1 decimal place, you would write it as 15.0, but it doesn't round up, so it's just 14.9. And then for scientific notation, this is where you want to write a really big or a really small number without all these extra zeros here. So this is the mass of the Earth. It's a really big number. This is the mass of an electron. It's a really small number. So instead of writing all those zeros out, we write it in scientific notation. So when you're writing a really big number or a really small number in scientific notation, you move the decimal until there's 1 non-zero digit on the left side of the decimal. So right now we have our invisible decimal here. So we're just going to move it until it gets to this point here, where there's 1 non-zero digit on the left side, and you count how many times you're moving it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So then I write it as 5.9736 times 10 to the power of 24. And I don't need to write anything after the 6 because none of those zeros are significant. It's a positive 24 exponent because we're starting with a really big number. If we're working with a small number like this mass of electrons, then our exponent would be negative.